Hi everyone, thanks for watching my presentation. My name is Shuai. I'm a PhD student at the University of Wisconsin at Madison. Today I'm going to present our paper, A Dichotomy for Real Boolean Holant Problems. It's a joint work with my advisor, Professor Jin-Yi. The Holant problem is a framework for counting problems. Such a problem is parameterized by a set of Boolean constraint functions, also called signatures, denoted by script f. Each signature f of right n is a map from the n-dimensional Boolean space to the complex field. An input of the Holant problem specified by script f is a graph where each vertex is labeled by a signature from script f. And for this graph, we consider all 0-1 edge assignments. Each assignment gives an evaluation which is a product of labeled signatures over all vertices. The output is the sum of products over all possible edge assignments. So this is the sum of product computation. Now let's see an example. A perfect matching of a graph is a set of edges, such that for each vertex, exactly one edge incident to it is selected in this set. In this graph, the set of red edges is a perfect matching. We want to count the number of perfect matchings of a graph. This problem can be expressed by the Holant problem parameterized by exact1 functions. Here is the definition of exact1 function. Such a function takes value 1 when the input has ambient weight 1, and it takes value 0 otherwise. Why we are interested in Holant problems? Well, the Holant framework is a very expressive framework for counting problems. Problems expressible as Holant problems include counting graph homomorphisms, counting constraint satisfaction problems, counting matchings and perfect matchings, and counting weighted Euler rotations. In addition, the computation of partition functions from many models from statistical physics, including the famous 6-word models and 8-word models, can also be expressed as Holant problems. It's proved that counting perfect matchings cannot be expressed by counting graph homomorphisms. So, Holant problems are probably more expressive. For any arbitrary signature set script f in a large class, we want to classify the complexity of the Holant problem specified by the signature set. Such a classification is usually stated as a dichotomy theorem for a large class of signature sets. The Holant problem is either polynomial time computable or it's Sharpe hard, with nothing in between. Sharpe is a quantitative version of the NP class. By a straightforward adaptation of Lander's theorem, we know that there is no dichotomy for the Sharpe class in general. However, for some counting frameworks, including counting graph morphisms and counting CSP, defined over general domain, 4 complexity dichotomies have been established. While for Holant problems, there are only limited results. Let's see some of these results. First, a dichotomy was proved for complex valued Holant problems when all signatures are symmetric. Well, we see a signature is symmetric if its value only depends on the Hamming weight of the input. By assuming some actual signatures, dichotomies were proved for some complex valued Holant problems, such as Holant star problems and Holant C problems. These are Holant problems by assuming some actual unary signatures are available. Without assuming any actual signatures, a dichotomy was proved for non-negative valued Holant problems. There are also dichotomies for some special cases of Holant problems, such as 6-word models and 8-word models. These models are Holant problems parameterized by a single 4-array signature. A dichotomy was also proved for counting weighted Euler rotations by assuming some symmetry condition. When a signature of orderarity is available, a dichotomy was proved for real-valued Holant problems. And in this paper, we prove a full dichotomy for all real-valued Holant problems, without making any assumption as we did in previous results. Now here we give a picture as a partial map for the classification program of Holant problems. The starting point is the dichotomy for the Boolean counting set P, and roughly speaking, there are two directions. One is to prove dichotomy for Holant problems by assuming some actual signatures, and the other is to prove dichotomy results for some special cases of Holant problems. The present result, the dichotomy for real Holant problems, is built on all these previous results. And as we will see, this is an arduous journey. Now, we first introduce the following classes of tractable signatures. The first class, denoted by T, is the set of tensor products of unary and binary signatures. So this class will be commonly used in this talk. There are also like product type signatures, affine signatures, and local affine signatures. And here, transformable means that these signatures can be obtained by a holograph transformation. It's known that the Holant problem specified by a signature set F is tractable when this signature set satisfies this tractability condition. Now, what we will show is that the Holant problem specified by a signature set script F is sharply hard when it does not satisfy this tractability condition. Thus, we get the dichotomy. In order to prove sharply hardness, we need to build polynomial time reductions. A commonly used approach is gadget construction. We see a signature, denoted by small f, is realizable from a signature set script f if there is a graph with some dangling edges, such that by labeling vertices in this graph with signatures from script f, this graph G, for example here, this graph G, defines this small signature f by its sum of products with dangling edges as variables. So for example, this gadget represents a small signature of 5. If so, then the Holant problem specified by this small f together with the original signature set script f is equivalent to the Holant problem specified by the original signature set script f. A simple gadget is a merging gadget. We will use this gadget commonly in this talk, and we connect two variables of signature using equality 2. Now suppose that a signature has relative n. By merging, we get a signature of relative n minus 2. Well, we know that when the signature set script f contains a signature of orderarity, a dichotomy is already proved. So we only need to consider the case that this signature set is a set of signatures of unarity. We suppose that it does not satisfy the tractability condition stated above. Then this signature set script f is not a set of tensor products of unary and binary signatures. So it's not a subset. It's not a subset of the tractable class T. Thus, it must contain a signature small f that is not in T. Now suppose that this signature small f has relative to n. Clearly, 2n is no less than 4. We want to prove sharply hardness by induction on the relative to n. The base case 2n equals 4 can be handled using the dichotomy results for 8-vertex models and counting weighted Eulerian rotations. Well, recall that the 8-vertex model can be represented as a Holant problem with a 4-array signature. Now in this talk, we only focus on the inductive step. The general strategy is that we start with a signature that is not in T, and we use it to realize a signature of lowerarity that is still not in T. If this can be done, then by a sequence of reductions, we can eventually realize a signature of relative 4 that is not in D. Then we are done by the base case. We use merging to realize signatures of lowerarity. Now, given a signature that is not in T of relative to n, we ask that by merging, can we realize a signature of relative to n minus 2 that is also not in T? Well, the answer is yes, but only for signatures of arity at least 10. There exist signatures of arity 6 and 8 with actual ordinary properties, which presented a formidable obstacle to the induction proof. So now let's take a look at these signatures. We consider the following 6-array signature f sub 6. This signature has the following expression. We can represent this signature by the following matrix. Here we use the first 3 variables as the row index and the last 3 variables as the column index. We use this picture to visualize this matrix. In this picture, a block with orange color denotes an entry +1, and a block with blue color denotes an entry -1. Other blank blocks are zeros. Like for example, here this orange block means that the value on the all zero input is 1, and so on and so forth. Now let's see some properties of this signature f sub 6. First, it's irreducible. Well, it's irreducible means that it cannot be decomposed as a tensor product. So clearly it's not a tensor product of binary or unary signatures. So it's not in T. However, by merging the signature f sub 6 using equality, we cannot realize a 4-array signature that is not in T. So by merging, we can only get signatures that are tensor products of binary signatures. And actually, we can prove that. Suppose that the signature set screw type does not satisfy the tractable condition, and it contains a signature of arity 6 that is not in T, then either the Holant problem is already sharply hard, or this special signature f sub 6 is realizable. So this f6 is an obstacle that we have to deal with. Now we want to show that the Holant problem, parameterized by this special f sub 6 together with the original signature set script type, is sharply hard when the signature set f does not satisfy the tractability condition. Now let's consider what other signatures can be realizable from this f sub 6. First, by merging 2 variables of f6 using equality, we can realize all 4 binary signatures. Here we give all these 4 binary signatures. Here this means the binary disequality. It takes value 1 when its 2 variables take different assignments, and it takes value 0 otherwise. These 4 binary signatures are related to Bell states in quantum information theory. Now, after we get all these 4 binary signatures, now we can use them to do the merging gadget. So we connect 2 variables of the signature f6 using an arbitrary binary signature. So now we consider 4 array signatures realizable from this special f sub 6 by merging each variables using arbitrary binary signatures. Well, if we could realize a signature of array 4 that is not in T by merging gadget using binary signatures, then we will be done because we still reduce to the base case. However, we can show that this signature f sub 6 satisfies the following Bell property. Well, we see a signature satisfies the Bell property if for every pair of indices I and j, and for every binary signature b, by merging variables xi and xj of f using this binary signature b, we get a signature which is a tensor product of binary signatures. Here we use this script B subtensor to denote the set of tensor products of binary signatures. So this property means that it's impossible to realize a signature of array 4 that is not in T by merging using binary signatures on this f sub 6. Actually, by modifying this signature f sub 6 using binary signatures, we can also realize other 6 array signatures that satisfy the Bell property. And we denote this family by script f sub 6. And we use this script b supertensor to the power of 3 to denote the set of tensor products of 3 biobinary signatures. Together, they capture all 6 array signatures that are a serious obstacle to our induction proof. So we have this lemma. Suppose that the signature set script f does not satisfy the tractability condition, and we also suppose that it contains a non-zero signature of arity at most 6. Then, if this signature, small f, is not a tensor product of biobinaries, and also if it's not in this family script f sub 6, then the Holant problem specified by small f sub 6 together with this signature set script f is sharply hard. So with this lemma in hand, if we could realize a signature of arity at most 6 that is not in the union between the tensor product of biobinary signatures and this special family script f sub 6, then there would be a more straightforward proof, because now we can realize a signature which gives us the sharply hardness directly. However, we tried many complicated gadgets using biobinary signatures and this signature f sub 6. We believe that all signatures of arity at most 6 realizable from biobinary signatures and this special small f sub 6, all these signatures realizable from this side, they are signatures in the tensor product of biobinary signatures, or it's in this special family, this script f sub 6. Now we have to come up with another way to prove the sharply hardness of the Holant problem specified by f sub 6 and 4 biobinary signatures together with this script f, which does not satisfy the tractability condition. Now, since it does not satisfy the tractability condition, it's not a set of affine signatures, so it must contain a signature that is not in affine. And we will prove, and we assume that this is the signature small f, and we will prove the sharply hardness by induction on the arity of this f. Now, why do we pick a non-affine signature? Well, notice that the tensor product of biobinary signatures and the special family, this script f sub 6, they are all affine signatures. So, if we have a non-affine signature of arity no more than 6, then we are done. So this is the base cases. Now we consider the inductive step. Given a non-affine signature, so this is another induction proof based on the arity of a non-affine signature. Now, given a non-affine signature of arity at least 8, by merging this signature using all these 4 biobinary signatures, can we realize a non-affine signature of low arity? Well, if this could be done, then still by a sequence of reductions, we would be able to realize a non-affine signature of arity no more than 6, and we would be done. In other words, suppose that by merging a signature f using arbitrary biobinary signatures, we can only get affine signatures. Then can we show that this signature itself must also be an affine signature? Well, for an affine signature, it satisfies the following two properties. First, all its non-zero entries have the same norm, and secondly, its support is an affine linear space. So we will prove that f itself is an affine signature by the following 3 steps. First, we ask that whether all non-zero entries of f have the same norm. Well, we can show that the answer is yes, but still only for signatures of arity at least 10. So for signatures of arity exactly 8, there do exist signatures which is not affine, and its entries have different, its non-zero entries have different norms, such that by merging it using biobinary signatures, we always get affine signatures. But for this signature, we can use it to realize some hard signature directly, so we can get the Sharpe hardness directly. Then, by assuming that this signature, all non-zero entries of this signature have the same norm, we ask that whether it has an affine support. Now this answer is yes. There is no counterexample here. And finally, we further ask that whether f itself is an affine signature. But still, the answer is yes, but only for signature of array at least 10. So there exist 8 array signatures that have that are not affine, but by merging it using Bell-binary signatures, we can only get affine signatures. Still, for these special signatures, we can get Sharpe hardness directly. So finally, we can show that the Holant problem specified by this special f sub 6, together with all 4 Bell-binary signatures, and with a signature set screw f that does not satisfy the tractable condition, we show that this problem is Sharpe hard. And then together we have that the Holant problem is Sharpe hard when the signature set screw type does not satisfy the tractability condition, and it contains a 6 array signature that is not in T. So now we are done with the 6 array case. Then we consider the case of 8 array signatures. Now we consider the following signature f sub 8. This is a 0, 1 value function. Still, we use the following picture to visualize this signature. Here, the first 4 variables are the row index, and the last 4 variables are the column index. And a block with orange color denotes an entry plus 1. Other blank blocks are zeros. Now, let's see some properties of this signature. So still, this signature f sub 8 is irreducible, and thus it's not in T. However, still, by merging it using equality, we can only realize signatures that are tensor products of binary signatures, which are in the class T. And in fact, this signature f sub 6 satisfies the strong Bell property. While we see a signature f satisfies the strong Bell property if for all pairs of indices I and j, and for every Bell binary signature B, the signature realized by merging variables xi and xg of f using this Bell binary signature B is a tensor product of the Bell binary signature B. So here, this is exactly the same B we used to do the merging gadget. Suppose that the signature set script f does not satisfy the tractability condition. Then we can prove the Sharpe hardness of the Holant problem specified by the signature f sub 8 and all Bell-binary signatures and the signature set script f, similar to the proof for the Sharpe hardness of the Holant problem specified by f sub 6 together with all 4 Bell-binary signatures and the signature set script f. If we could realize all 4 Bell-binary signatures from the signature f sub 8 by Gadget Construction, as we did for the signature f sub 6, then we would be done. However, since the signature f sub 8 has even parity, which means that all its non-zero entries are uneven weighted inputs, and all its non-entries are non-negative, we can show that all gadgets realizable from the signature f sub 8 have even parity, and they have non-negative entries. Thus, it's impossible to realize the other 3 Bell-binary signatures by Gadget Construction from the signature f sub 8. And in the proof, we give a non-constructive reduction to realize Bell-binary signatures from the signature f8. This reduction is crucially based on the strong Bell property of the signature f sub 8. Then, finally, we can prove that the Holant problem is Sharpe hard when the signature set screw type does not satisfy the tractability condition, and it contains a 8-array signature that is not in T. Now let's summarize the proof for the real Holant dichotomy. Now we only need to prove that the Holant problem is Sharpe hard when the signature set screw type does not satisfy the tractability condition. And we know that if it contains a signature for auto-arity, then we are already done. So we only need to consider the case that this signature set consists of signatures of unity. And since it does not satisfy the tractability condition, it contains a signature small f that is not in T. And we suppose that this signature small f has relativity to n. We know that 2n is no less than 4. And when 2a equals 4, 6 or 8, then we are done by all these previous lemmas. So these are the base cases for the induction proof. And when 2n is larger or equal to 10, then we can show that the inductive step works. So we can eventually realize a signature of arity no more than 8 that is not in T. Then we are done. So in this paper, we proved a dichotomy for real-valued Holant problems. Well, the ultimate goal is definitely a dichotomy for complex-valued Holant problems. In order to achieve this result, we think that we need to first generalize the dichotomy for real Holant problems, where an ordinary signature is assumed to be available, to complex-valued Holant problems, where we still assume an ordinary signature is available. Also, we think we may need to generalize the dichotomy for counting weighted orientations with a symmetric condition to the general counting weighted orientations without this symmetric condition. So this is my talk. Thanks.